Good morning, my lovely 13s. Right, buddies, here we are again in the second lesson now of our lessons on differential equations. And this is the lesson where it starts to actually become quite cool and quite like calculus-y and a bit more pure mathsy, which gets me really excited. So I'm really quite pumped about it. Today's lesson is called Separation of Variables. So if you want to pop that title into your notes, that would be good. And the topic that we're going to do today is actually from regular year 13 maths. But then following this lesson, like the next lesson and onward, we're going to be properly in further maths territory. So that's also very exciting. Cool! Now essentially, buddies, when you get these differential equations, so we have a dy dx equaling xy squared in this first one. When you get these differential equations, and there's nice simple ones like this, it's just one thing times by another thing. There's no constant number on it. There's no bizarre other functions involved. It's just an x and it's just a y squared, and they're just touching. It's sometimes possible to get the general solution or the particular solution without too much effort. Yeah, you can just kind of get it in a few steps, which is what we're going to do today. So let's do it. Let's write out the first question, buddies. Let's do it. Okay. So here we go. dy dx equals xy squared. I'm going to go for the general solution. Now the general solution, one more time, is it'll be like having y as its subject, or it'll have an equation with x and y in, but there will also be a plus c. It's the one that's got like the whole family of curves, like the general solution back from the previous slides. The general solution could be any one of these blue parallel curves to one another, whereas the particular solution could be this one, okay? So we're going to get the family, not the exact curve that we're after. So yeah, here we go. The strategy for these intro ones is just this. If you check it out, our equation has x in it, and it's also got a dx in it, and it's also got y in it, and it's also got dy's in it. Now, in order for the separation of variable method to work, the way that it works is you end up trying to split up your equations such that the x's are with the dx's and the y's are with the dy's. So we're going to break up our derivative and we're actually going to split it from itself, which in its, we're going to split it up, the dy dx, which in itself is a bit strange because dy dx does have a meaning. It's an instantaneous change in y with respect to x, so it's a gradient at a particular point. So in theory, kind of like dx is kind of like 0. So it's weird that it's weird that you'd split them up, but it does work. So it's a cool strategy. So let's try it. Cool beans. Here we go. Yeah, so we're going to want to rewrite it so that the x's are with the dx's and the y's are with the dy's. Well, here's what I'm going to do. I'm going to times dx up to be with the x, and I'm going to divide y squared down to be with the dy. So what you're going to find is that you're going to get 1 over y squared dy equals x dx. Happy days with that, buddies? So I treated it algebraically, even though it's a calculus question. I did kind of just approach it algebraically, as these were just as you would kind of a constant number, or a 3 or a 5 or whatever. I just times up to make it work. Now, it's bizarre written like that. It's not quite accurate, but here's what you can do. If you just whack an integral sign onto both sides, that's going to be your trick to solving it, okay? So we've kind of formulated two integrations for us to conduct or to carry out here, and that's your trick, and you've got it solved after that. So let's do it. Right then. So instead of 1 over y squared, I'm going to write this as y to the power of minus 2 dy. So it's the integral of y to the minus 2 dy, and just leave this as it is, x dx. And you carry out the integration. This is the integration of y to the minus 2 with respect to y, so the variables match up. So raise the power by 1, y to the power of minus 1, and divide by the new power, divide by minus 1. And you're going to get an integration constant of plus c, but I'm going to get one over here as well, also of like, say, plus d. So I'm going to cut to the chase, and I'm going to say those two integration constants together may as well be modeled as 1, and so that's what I'm going to do in a sec. So on this side here, x just becomes x squared over 2, right? Now I'm going to put the plus c here. Now in theory I could have had the plus d here as well, and then I could move that over. The constant on this side would be like c minus d, but then I could say let a equal c minus d and not bother. Do you see what I mean? That this is, yeah, we're on to a winner with this. We'd just rather have one constant rather than two, because I'm just going to combine them together anyway. Cool. Let's make y the subject just to see how we get on with that. So this is the same as like -1 over y equals x squared, or x squared over 2 plus c. What I'm going to do is I'm going to then, what do I want to do? Do I want to times both sides by 2y? Can I be bothered with that? Do I want to do that? Yeah, should we? Yeah, okay, let's do it. So let's do it. Okay, times both sides by 2y, because let's just not bother with the fractions. And we're going to get on this side then. It's going to be times 2y, times 2y, times 2y. And we're going to end up with this. We are going to get -2 equals, and we're going to get here, cancel, cancel, x squared y plus 2yc, and yeah, go on then, let's make y the subject. -2 is equal to y bracket x squared plus 2c, and that means that y is going to be like -2 over x squared plus 2c. C is just a constant, so I'm going to be like, because we don't know what that constant is anyway, we're gonna have to work out what that constant is anyway. I'm gonna let let's go with D. Let D equal to C. That way you're gonna get y equals -2 over x squared plus D. Bish bash bosh. You just figured out the answer to our differential equation. So you've put it in a form that is lovely, that is finished, and hooray! Bish bash bosh, my lovelies. So good work. On to the next question. And here we go on the harder difficulty ones. Now, this was not actually super, super difficult, but it's just one of those ones where it gets a bit more weird with the modulus sign. So they're gonna, it's got a trick to it, a modulus sign trick, and that's why this question's a little bit harder. But we're gonna be good at it, so no problem at all here. It says this: a drink is placed at room temperature where the ambient temperature is 20 degrees Celsius. So essentially it's in a room that the temperature is 20 degrees Celsius in the room. And a model for the subsequent temperature T of the drink at time T. So if we have capital T and we have little t, nightmare to the same letter in each one, but that's okay. In hours is given by Newton's law of cooling. This leads to the differential equation here. And it says then that find the solution of this differential equation in the cases where temperature is 80 when time equals 0, and temperature is 0 when time equals 0. Okay. Now this question does start off just the same as the others, and pretty much I think you could probably pause the video and get ahead of me, but get it down to where you've got the modulus part as the left-hand side, as the subject, okay? So get the modulus part of the left-hand side, but then don't go on from there, because there is something, yeah, it is a trick question, essentially, so I want to make sure that you don't fall for the trick. So if you want to push pause and try to get down to where the modulus part is the subject, that'd be amazing, and pause now, go. Or if you wanted to stay with me, let's do it. Okay, so if you're with me, here's what we got. First things first, it says that dt, like derivative of temperature with respect to time, is -5, temperature, take away 20. We're going to do our same old trick, so we're going to try to get all of the capital T's with the dt's, and we're going to get the little t's, of which there actually isn't any, with the dt's that match it. So here we go. I think we're going to get this. I'm going to divide the t minus 20 down, that bracket down, and I'm going to get this. I'm going to get 1 over t take 20, and I'm going to leave the big capital DT there, and I'm going to times the little dt up and get -5 dt here. Next step, we're actually trying to get a general solution. We're actually trying to get rid of the differential equation, so we're going to integrate to undo the differentiation, and here we go. Here's where it gets a bit wonky. It's 1 over t take away 20. Now, this is just linear on the bottom, okay? So it's just the same as 1 over t. There's not like a chain rule issue. There's nothing to worry about. And so this just becomes this. It becomes ln of modulus of t take 20. on the left-hand side. Now, you didn't have to divide it by 2 or 3 or anything, because there wasn't like a 2 or a 3 touching the t. There's no chain rule issue. Needs an integration constant, but because I'm doing the other side anyway, I'm going to pop the integration constant on that side. Now, here we go, minus 5 dt. That's just going to become minus 5t. And now I'm going to put my integration constant in plus c. Cool. Now, we're not going to mess about with the modulus yet, so let's do that thing. Let's get rid of the ln. Let's raise both sides to the e, because it's secretly base e. So we'll go e to that side equals the t take 20. So we're going to get modulus t take 20 equals, and this is going to be e to the minus 5t plus c. You might be thinking to yourself, is there a better way of writing that? And you say, yeah, of course there's a better way of writing it, because we don't like plus and minus. It's difficult to know what that plus c is doing in the power. So we're going to do that thing with the a like last time. We're going to use the index laws and split it down. So here we go. T take 20, and then this is going to be e to the minus 5t, e to the c. Now, this is just a number raised to a number, so you may as well replace it with just its own variable. So t take away 20, and I'm just going to let e to the c equal capital A. And then I'll have a e to the minus 5t, bish, bash, bosh. That's the general solution, but I can't go further yet, because this question, the modulus actually does make a difference, okay? Remember in the last question, all we did was like, oh, well, because the population started at 0 and it got bigger, t could never actually be negative, and then therefore, there's only the one variant of the modulus to worry about. This question, we're not so lucky, because if you look at part I, it starts off with the temperature being 80 at time equals 0, which means you go 80 take 20, which is 60, which is positive, right? So in the case of I, you could ignore the modulus symbol, but in double I, if you look at this, temperature is 20 or is 0 when t is equal to little t is equal to 0. Now in that one, if you did 0 minus 20, you'd get a negative number, which the modulus would force positive, which means that we have to kind of resort to that weird definition of modulus. So it's a tricky one just because of modulus, but I'm gonna make it really clear, just in case I'm not sure if you guys all remember how modulus works. Okay, basically, what a modulus is, you guys, I bet, know that if you get a negative number, what the modulus does is it switches it positive. I think that everyone will know that. Now, here's the reason why. It's essentially like this. Here's the definition of modulus. Say that, oh god, here, oh, can I remember? Yes, I can. Here we go. Modulus of x is like equal to x if x is greater than or equal to 0, okay? That's what the definition of modulus is. But the modulus of x is equal to negative x if x is less than 0. Strictly less than 0. So in other words, when x is negative, you put a negative in front to switch it positive. That's actually what modulus is doing. Now, if you think about how that applies to this question, so I don't know if you do know that, I hope you know that, but just in case you don't know that, let's see how that applies to this question. That means, what I just said there, that means that this actually has two potential general solutions. One of them is this. One of them is going to be t take away 20 equals a e to the minus 5t. And that's if you found yourself in this scenario. That's if you found yourself in the positive scenario. So does that make sense, my buddies? That if we didn't actually have to use the property of modulus to negative things, you get that. That's if you ended up in the positive scenario. Now the thing is, you could have ended up in the negative scenario too, in which case t take 20, you'd have to introduce a negative here. There it is. You'd have to introduce a negative in order to force this side positive. So that's the, ooh, my thingy's in the way. You can't see that, but I can see it. Something just jumped on my screen. You'd get this. You'd get a e to the minus 5t. Now that's in the negative scenario, okay? That is as though we've used that one. We've had to make the right-hand side negative because we ended up in that scenario with the modulus. This is why this question's a trick question, because we have to actually be wary of that. Okay, now from the black, because this part's just extra, just drawn there, but from the black, the modulus of t take 20 equals a e to the minus 5t. We're ready to go for our general solution. So for part I, it says when t is 0, big T is 80. So in other words, it starts off as positive. Just work with the black, okay? Work with, I'm going to highlight it even to show you it's important. Work with this. This is our general solution, not the stuff I just drew below. I just drew that to help you understand. That is our general solution that we're dealing with. So here we go. Pop your numbers in. So it says that big T is 80, so we're going to, on this side, have modulus 80 take 20. And that's going to equal A, E to the minus 5t, but t is 0, so it's just A, E to the 0. Okay, that means this side is modulus of 60. Oops, square this straight thing, I mean. Modulus of 60 is going to equal A. Okay, now here's where it gets weird, okay, buddies? 60 is positive, right? Therefore, the modulus isn't going to have any impact at all. We are in this scenario, because we didn't need to put a negative in. 60 was already positive, okay? So straight away, A is 60, no problem at all. And we ended up in the top scenario, which means we're going to end up here on the positive scenario, because we didn't actually have to switch the 60 over to being negative, which means we use the top variant of it. We use the positive variant of the modulus. So we're going to write this. We're going to write t take 20, without the modulus, we've been the modulus now, is going to equal 60e to the minus 5t, and then just make t the subject. T equals 60e to the minus 5t plus 20, and that is your final answer. I hope you understand why it was that top version, and again, if you didn't understand why, it's because we didn't have to actually switch the sign on the 60. It was already the correct positive sign, which means we were in the top scenario, that the modulus didn't need to do anything, and so that's why it's that. Cool beans. Now, in the second one, that might differ. Spoilers alert, let's see. In the second one, here's what we've got. We've got that when little t is 0, at time 0, our drink is 0 degrees Celsius. So actually, our drink is starting from frozen and it's going to warm up. Okay, same deal, into the black, into the part I've highlighted in yellow, like the asterisk black line, the general solution line. Well, let's do it. What we're going to get on this side is 0 take 20, because big T was 0. And on this side, we're going to get A, E to the 0. Cool. That means you get modulus of negative 20 equaling A. But here we go. That's negative, right? And modulus switches it positive. Well, here you go then. A is certainly positive 20, because it just got switched positive. But what scenario did we just find ourselves in? Where did we just find ourselves? Did the modulus need to make something negative? Did we have to apply a negative to get the minus 20 to be a 20? Well, yeah, we did. We're in this scenario this time, buddies. The negative scenario. Which means in our equation, in our yellow, we're going to choose the negative variant. So we're going to go into the negative this time. So from the red, we're going to go t take 20, but because we actually did have to use the modulus, we're going to take the negative. Negative. I'm taking it from this bottom one because we did actually have to apply the modulus. We had to apply that negative property of the modulus. And then it's going to be minus 20 e to the minus 5t. So there's where we are. And then just rearrange it. T equals 20, take away 20, e to the minus 5t. Bish bash bosh. That's the answer. I hope that you understand that modulus part, because I think that that's the weirdest. Essentially, if you've had to use the property that moduluses can apply a negative, then you're going to have to take the negative variant. If you didn't need to use that thing, you can just pretend as though the modulus isn't there, and you can just use it as though the modulus weren't there, the positive variant. And that's it. So I hope you get it. Give me a shout if you don't get it. I really hope you've learned how modulus works already. I think you have. I think the timing of this lesson is right that you already know how modulus works, but also give me a shout if you don't know how modulus works in the chat, and that'll be really good. I want you to do page 190, question 1 to 13. It is worth probably doing a couple of easy ones, like of the question 1 and 2, but don't spend a ton of time on that, and then try to get onto some of the later questions because they are the ones where they're using this weird modulus trick, okay, that you need to kind of be alert to. So, yep, little mix from there. You've done really, really well. Keep up the awesome work, my lovely 13s, and yeah, take a picture, submit your work when you're done, and that's it from me, and see you next time. Bye, buddies!